Thank you very much for a kind introduction. I'm Keisuke Minagawa from Saitama Institute of Technology, and I'm also the chair of panel of elevator safety and reassurance, Japan Society of Mechanical Engineers. So today I want to introduce our activities in this panel, and I'd like to share the outcome of the rope vibration analysis working group. So let's start with introduction. As you know, Japan, we have a lot of earthquake because Japan is located on the west side of Pacific plate. I'm sorry, this map comes from Japan. So Japan is located on the center.
Of course.
And there are interesting data regarding Japan earthquake. The area of Japan and the surrounding is only 0.1% of whole Earth. However, 21% of the earthquakes that have the magnitude more than 6 occurred, and also the 10% of seismic energy is dissipated in Japan and Earth surroundings. So we have many experience of earthquake. So next slide shows the example of damage of lift by actual earthquake. And this shows the damage ratio of lifts. This is the data from Kobe earthquake in 1995, and this is the Great East Japan earthquake, so-called Fukushima earthquake, and the Kumamoto Osaka Northern earthquake. As you can see, the main cause of the damage by earthquake is rope catching. So, and also this kind of large vibration of rope is induced not only by earthquake, but also by strong wind, by typhoon or hurricane, something like that. So, and in addition, these accidents will induce passenger trapping in cars. So, it should be prevented by the technology. So, the first step in preventing rope catching by earthquake or strong wind is to properly estimate the vibration response of the rope by simulation analysis. But it requires a high level of expertise. So maybe it is difficult to calculate for the small lift company. So the rope vibration analysis working group in the Japan Society of Mechanical Engineers was established to investigate analytical methods of rope transverse vibration and to share and to develop knowledge regarding rope vibration analysis. And the final goal or final aim of this working group is to improve the technical skill of the lift industry, of course. So what is the rope vibration analysis working group? The rope vibration analysis working group is a part of panel of elevator safety and reassurance. That is, I am the chair of this panel in the transportation and logistic division of the Japan Society of Mechanical Engineers. And the Japan Society of Mechanical Engineers is largest society regarding mechanical engineering in Japan. So we have a very long history from 1897. And also the Japan Society of Mechanical Engineers has more than 30,000 members. And the rope vibration analysis working group is active from 2015 to 2021. And the working group has about 10 members, including engineers or researchers from lift manufacturers like Mitsubishi, Toshiba, Hitachi, Fujitec, and the university like me, So what we did is, firstly, we investigate what kind of analytical method has already proposed. As the literature survey of lobe vibration analysis method, we found 4 methods like this table. That is, method based on wave equation and the single degree of freedom model and the multi-body dynamics and the finite element method. From the viewpoint of accuracy, the method based on wave equation and multi-body dynamics and the finite element method has very high accuracy. However, the multi-body dynamics and the finite element requires special parameters like a spring constant between the point to point of the wire rope to calculate the response. And also, they require special software to calculate. So in our working group, we apply the wave equation to calculate the vibration. And also we done another literature survey regarding damping ratio of wire rope. And we found that the wire rope has only 0.2 to 0.4% of damping ratio. So this is very small damping ratio. So next, we actually conducted vibration response analysis based on the literature survey. The modified wave equation for the lift lobes was applied for our analysis. And this modified wave equation is considered tension distribution of the weight of lobe itself. This means the top of the lobe has tension not only by the weight of car, but also by the weight of lobe itself. And on the other hand, the bottom of lobe we don't need to consider the weight of lobe itself. And also the changes of tension is also considered. I mean, if the lobe transversely vibrate, the car will move like vertically up and down if we don't consider elongation. So the tension of lobe changes by inertial force of the vertical motion of car. So the wave equation for lift lobe will relatively difficult compared with ordinary one. And this slide shows the formula for the natural frequency and the parameter of a lobe. We consider lobe with 50 meters in length. And first of all, we compare the method based on the wave equation without vertical motion of car with a single degree of freedom model like this, and modal model. The modal model is the combination of the single degree of freedom model. The natural frequency of single degree of freedom model was calculated using the equation, this equation. And the sinusoidal wave was inputted like this animation. And we changed the frequency of the input wave from 0.5 to 1.5. And the vertical axis indicate the amplitude of lobe. As you can see, both single degree of freedom model and the modal model represented well the result of the wave equation. So maybe we can use the single degree of freedom model and modal model to rough analysis of the vibration. However, if we consider influence of vertical motion of car, the amplitude and the frequency at resonance condition decreased as the input displacement increased. The difference of the line indicate the difference of input displacement. As you can see, if the input displacement is large, the amplitude is reduced. And the final slide, final graph shows the result of seismic response analysis. This graph shows the relationship between input displacement and response displacement, and both horizontal and vertical axis was changed and dimensionless value by using rope length and the maximum input displacement. And these lines are the result of sinusoidal wave input, and these plots indicate the result of the seismic response analysis. In addition, the solid plot showed the result with vertical motion of car, and the open plots indicate the result without vertical motion of car. As you can see, there are few differences between the with or without vertical motion of car in case of seismic response analysis. And also the response of seismic response is smaller than the response of sinusoidal wave. So if the resonance response in sinusoidal wave was considered, it will be safety for the seismic response. So finally, I'd like to conclude my presentation. In this presentation, I talked about the activity of the rope vibration analysis working group, and we can find that analytical method based on the wave equation, and analytical method based on the wave equation is very high accuracy, and also single degree of freedom model are suitable, applicable for the rope vibration analysis. And the damping ratio of lift rope is very small. Thank you very much. That's all.